Hello, AP Physics C students. In this video, I'm going to go through the main methods of deriving potential equations from our continuous distributions of charge, and I'll talk about how we decide which method to choose. Now, if you want to just sit back and watch the video, that's great. If you want to take your notes, that's fine. But in the end, I'm actually going to publish the end slide for you, so you really don't have to take notes. This is really just for you to sit back and absorb. Okay, so there's basically two different ways we have of doing our potential equations. We have adding up little bits of dV or integrating the electric field equation. Let's first look at adding up dV. Is our basic idea that every little bit of charge along the distribution of charge contributes its own little bit of potential. We're just adding it up, we're integrating those little bits together. So it's just, dV equals k dq over r, integrate both sides, great. Okay, now remember, we talked about this idea that where appropriate, you're going to integrate towards a higher potential or up the mountain or against the electric field. I say where appropriate because sometimes we're not looking at a change in position, right? Sometimes we're looking at a fixed position and we're just integrating all the bits around. Other times we are looking at different distances away from it. So it depends on what you're doing there. So, sometimes it matters, sometimes it doesn't. But when it does matter, you're going to integrate towards higher potential. For integrating electric field, well, you have to already have the electric field equation, and here's this version, delta V equals the negative integral of E dot dr. Let's remind ourselves that it is a delta V, right? There's a change of potential so critical that it's a change of potential, and so it's often written this way, VB minus VA equals negative integral of E dot dr. And then it's really essential you define your limits of integration, right? We always go final minus initial. The final goes on top, the initial goes on the bottom, so this is integrating from A to B. Once again, you're going to integrate towards higher potential. So A should be the lower potential, B should be the higher potential. Now, sometimes you need the delta V. Other times you need a function of V as a position of R, as a function of R, right? And so to do that, you have to know the value of V at some point, at the starting or the ending point. You have to either know VA or VB. Right, so sometimes this is infinitely far away, like V approaches infinity, it goes to 0. Other times you need to define a 0 point, or perhaps you need to know the value of V perhaps on the surface of the object. We've done that before, for example, when we did like the potential inside the insulating sphere. You had to know the potential on the surface of the sphere, and that became either VB or VA, depending on which way we're going, depending if we're going whether there's a positive or negative charge creating the field. But again, sometimes you don't even want a potential function. Sometimes you just want to know VB minus VA, in which case you just leave it as that. You leave it as a delta V, and that's fine as well. Now, how do you decide which method to choose? It's all about what's easier, right? So we would choose this method when you can easily identify little bits of dq to integrate. Sometimes that's not as easy to do. Sometimes you can't figure out all the different distances between the point you're looking at and all the bits of dq, in which case then you go over to this side. And you might recognize this is very similar to when we decided whether to use Gauss's law or not. So really, you tend to use this right-hand side method when you would have done Gauss's law. So if you would have done Gauss's law to find E, then use this method to find V. And again, all this will be published for you as a notes page.